Cooperstone, and this is my Physics 2211 Lab 3 about black holes. So the goal of part 1 of this lab is to find the mass of a black hole, considering how it interacts with a star orbiting around it. And the second part involves finding the initial velocity required of a ship to pass by close to the black hole and exit without getting sucked into it. We assumed there were no other external forces, and the findings were that the black hole mass was about 1.3 times 10 to 34 kilograms, and the initial velocity of the spaceship was negative 3.75 times 10 to the 7th meters per second, the x component, and about 2 times 10 to the 6th meters per second, the y component. Newton's second law of motion is included, which is that force equals mass times acceleration, which equals the rate of change of momentum over time. And then the position and velocity update formulas altered to not include acceleration in the position update formula because the new velocity is found in every iteration, so acceleration is not needed. Gravity is also used with the law of universal gravitation and the universal constant gravity, along with r hat, which is the distance between the two objects divided by the magnitude of the distance. And then you can adjust the universal law of gravity to solve for the mass of the black hole as seen below. And finally, we use the concepts of separating rate of change of momentum and therefore force into parallel and perpendicular components, where the parallel component represents the change in magnitude of momentum, whereas the perpendicular component is just the change in direction of the momentum. So we look at the system in part 1, it's just the planet and black hole interacting, exerting equal and opposite forces on one another. And then in part 2, the planet and black hole, as well as the ship, are all in one system, each exerting a force of gravity on the other that is equal to what the other exerts on it. So part 1, we find the mass of the black hole. Here are the initial conditions. You can see the star mass, the universal gravitational constant, and then the time steps, with each time step being 1 day in seconds. And then the calculation loop, where I said find initial and final velocities and momentums, as well as finding the change in momentum over time, which I set equal to net force, and then finding the parallel and perpendicular components. Find the parallel component by applying this to p hat, or the unit vector of momentum, and then subtracting that from the net force to find the perpendicular change in momentum, or the perpendicular component of force, because the parallel and perpendicular components summed is the net force. And then here you can see that I found the black hole mass to be about 1.3 times 10 to the 34 kilograms. And here's the video of my simulation being run. And as you can see, it goes in an elliptical pattern. And the mass was found by summing all of the values seen generated and then finding the average of them. And the magnitude of the net force and the parallel and perpendicular components can be seen there, given at the end of the code. So the planet clearly follows an elliptical orbit around a black hole, ending where it started. And momentum was used to find the force because the mass was unknown. The force was non-constant, resulting in non-constant acceleration. And potential sources of error include the estimates of the black hole varying due to rounding errors. In the second part, we aim to find initial velocity so that the ship does not crash into the black hole. Here you can see the initial conditions with the new black hole mass found in part 1. And then here you can see the loop where I found r and r hat, and then use this to find the forces of each object on one another, and then find the net force on the planet and on the ship, and then model the velocity and positions after those forces. And here you can see my simulation being run, and along with it, the initial velocity required to get as close as possible, clearly with sharp change in motion. And I simply tried different values until it worked, and the smallest distance was found to be about 2.74 times 10 to the 8th meters. So ideally, this would have minimized the distance between the two, but obviously since I was plugging in numbers, this is not achieved. The x component velocity was negative because it was moving to the left, and the y component was positive because it was going slightly above it. And the fact that the spaceship continued without stopping showed that it achieves escape velocity. In this case, sources of error, again, are rounding errors. So in the what does it mean question, momentum is equal to an object's mass multiplied by its velocity, and when you divide that by time, that gives you mass times acceleration, or force. So that means the net force is equal to the rate of change of momentum, and therefore splitting that rate of change of momentum into parallel and perpendicular components also splits force into parallel and perpendicular components, meaning those components are equal to one another in both force and momentum. And for the what if question, I was able to achieve orbit around the black hole, and I knew this to be the case because I allowed the simulation to run and it kept following the same orbit, a more elliptical orbit than circular, as seen in the planet. And the initial velocity in this case, the y component was greater than the x component because I had to go almost vertically and then slowly kind of travel around the black hole instead of heading straight towards it like in part 1. And that is the end of my lab.